What's up guys, Stephen Gong here. It's March the 3rd, 2018 and we have a beautiful day here in Oakville, Canada. Right now we're beside the Lake Ontario and we'll have a serious topic about a physicist named Walther Meissner today. So he basically the one who pushed forward the development of superconductivity. But first off, what is superconductivity? Please allow me to explain. Come on. So now imagine the roads are made of the superconductors at room temperature. That means the cars with hover will be run over the street without even touching it, without using any gasoline whatsoever. So what if the belt you're wearing is made of the superconductors? Then you'll be floating in the air just like the Superman, floating over the magnetism. So this is the realization of an ancient dream of flying in the air, of going against gravity, anti-gravity. And this is how we use magnetism to counteract the force of gravitation. So the objects that are levitating in the air are called superconductors. Superconductivity is a quantum state of matters that only occurs below a certain critical temperature. And there are two main properties of these superconductors. First one being the zero electrical resistance, and the second is the explosion of a magnetic field from the interior of the superconductor. Caught below a critical temperature, certain materials display astonishing characteristics. They can be made to levitate to present no electrical resistance and thus conduct electrical current with zero losses. Materials that possess these properties are known as superconductors, and they are vital of creating the strong magnetic field required for techniques such as MRI. But to unlock superconducting properties, it is necessary to cool the material down to below minus 150 degrees Celsius. Two men has done fundamental research which have paved the way for advances in this field. The first one is Kamalain-Onnes, who created the coldest point on the planet, using the liquid nitrogen to conduct experiments. Absolute zero, minus 273 degrees Celsius, is defined as the lowest temperature physically possible. Atoms have a certain kinetic energy which is dependent on the temperature. The colder it is, the less they vibrate. At absolute zero, nearly all atomic motion ceases. Another interesting finding is that the resistance doesn't decrease gradually. It disappeared abruptly when a certain temperature was reached, and this temperature, when the substance suddenly enters the superconducting state, is known as the critical temperature. Electricity is the flow of electrons inside the material. What Ohm called resistance is the degree to which the cable impedes an electric current running through it. Resistance occurs as a result of electrons colliding with the atoms of the conductor and giving off energy in the form of heat. The more energy is passed to the atoms, the less kinetic energy remains for the electrons, and the greater the resistance. This is when Walther Meissner comes into play his role. Walther Meissner was born on December 16, 1882 in Berlin, and his father, Waldemar Meissner, was an engineer. His family background has initiated his profound interest in physics and research in the first place. Meissner started out studying engineering at the Technical University of Charlottenburg, but just before taking his exams, he switched to Berlin University to study physics and mathematics. He later studied mechanical engineering and physics at the Technical University of Berlin from 1901 to 1904. His doctoral supervisor being Max Planck, the well-known originator of quantum theory and won the Nobel Prize in physics in 1918 for his discovery of energy quanta. Along with Meissner, Max Planck has taught excellent students. Meissner later referred to Max Planck as someone who created himself, and the influence Max has made on him is considerably crucial. 2 years later, Meissner went to work for the Imperial Metrology Institute, where he was initially assigned responsibility for verification and research projects. From 1922 to 1925, he built a helium liquefying facility, the third of his kind, worldwide apart from Leiden and Toronto. The liquid helium produced in it was available for low-temperature research. In 1928, a low-temperature laboratory was set up and equipped from the atomic research, and Meissner was made its director, and the same year he was promoted to the higher civil service, and in 1930 qualified as the university lecturer in Berlin, and his subsequent research and development work earned Meissner a reputation as an experimental physicist. Together with Robert Ossenfeld, he discovered the phenomenon now known as the Meissner Effect, a major discovery about superconductivity. In 1933, the two men showed that superconductors are not just perfect conductors, they also expel all magnetic flux from their interior. A superconductor is thus a perfect diamagnet. A permanent magnet creates a magnetic field. If a diamagnet enters the field, it will try to keep its interior free of magnetic flux. To do so, the diamagnet generates a magnetic field of his own, directly opposed to the field around it because of the reciprocal repulsion of the field. A superconductor can thus levitate over a magnet. The spontaneous creation of a magnetic field is the Meissner effect. The phenomenon is related to the generation of screening current around the surface of the superconductor that are able to cancel out the magnetic field. Notably, the Meissner effect may not be observed at all times. When the external magnetic field is too strong, the internal superconducting ability may not be expressed. Therefore, there will be no effect at all. And sometimes, when there has the intermediate forms of the magnetic field, then the induced magnetic field will not be strong enough to be expressed fully, and then there will only be expressed partially. The size, the shape, and the content of impurity of the superconducting material can all affect its ability to express itself. And visually, we can observe this effect by putting a magnet over the superconducting material, causing the magnet to levitate. He was examining the magnetic properties of materials as they became superconductive, a condition met with as the temperature of the element or compound falls below the critical point. It was found quite unexpectedly that if the solid lead sphere is placed in a magnetic field and the temperature allowed to fall below the critical temperature, the magnetic field expelled from the sphere which became perfectly diamagnetic. The presence of the Meissner effect is now used as a routine test for superconductivity. The Meissner effect is the expulsion of a magnetic field from the superconductor during a transition to the superconducting state. The samples, in the presence of an applied magnetic field, were cooled below their superconducting transition temperature, whereupon the samples cancel nearly all interior magnetic fields. They detected this effect only indirectly because the magnetic flux is conserved like superconductor. When the interior field decreases, the exterior field increases. In 1933, the two researchers published their findings in an article headlines "A New Effect of Superconductivity." A year later, Meissner was awarded a professorship at Munich Technical University and became director of the Technical Physics Laboratory. During the Second World War, the low-temperature laboratory was evacuated to Hessen in Upper Bavaria, where it was accommodated in temporary hunts. After the war, Meissner was appointed the Dean of the Technical University's General Science Faculty and rebuilt the Technical Physics Laboratory in Munich. In 1946, he was appointed director of the Academy's first low-temperature research commission. But despite intensive research, the underlying mechanism of superconductivity remained elusive. Even today, we have no explanation, just theories. Extreme cold changes the way the atom in the crystalline structure of the superconductor vibrates and neutralizes the repulsive force that normally exists between electrons. Electrons are paired and formed a current that is able to flow without experiencing the least resistance. For this theory, physicists John Barton, Leon Cooper, and John Schaffer were awarded the Nobel Prize in 1972. For Walther Meissner, this was the reason to continue his work at the Central Institute for Low-Temperature Research, which he established again next Munich. He experimented there till a very old age. He lived alone with his two dogs for the last several years of his life. On the 15th of November, 1974, Meissner died in Munich. On the 100 years anniversary of his birth, in 1982, the Institute for Low-Temperature Research located in that city was renamed the Meissner Institute in his honor. After that, scientists seek to find superconductors that does not need to be cooled to such low temperatures to become superconductive. High-temperature superconductors are materials that superconduct at temperatures above minus 196 degrees Celsius, a feature that enables them to be cooled by liquid nitrogen rather than helium. This increases the range of practical applications of superconductivity because liquid nitrogen is far more widely available and much easier to handle than helium. Unlike many other scientists who have made contribution to the development of superconductors, Meissner has not received enough recognition, such as the Nobel Prize or any other awards that has been awarded to other scientists. People from other countries even refer to honors all the time because he was the one who discovered the first superconductors, and prizes over the other scientists who has found those high-temperature superconductors after Meissner. However, he devoted his entire life to the experiments of low-temperature substance, and leaves all the outside world and comments aside. What he cared about is not the fame and reputation he collected over his life. What he cared about is the contribution he can make to creating a better world. The application of this zero resistance characteristic will provide high energy efficiency in the transportation by providing the energy transfer with no energy losses. Moreover, the characteristics will also provide high energy efficiency in the renewable energy resources, and the application of the quantum locking can provide extremely fast transportation to humanity. Through the use of these applications, humanity will be freed from forcibly using upon the non-renewable energy sources, and the superconductors will bring us to a way brighter future. Please let us know what you think about this video by leaving a comment below, and we will see you next time. Peace out.